Okay, hi everyone. So welcome to Maths 30 again. For this video, we'll discuss the vector functions. To be specific, we will start with the vector spaces, vector functions and space curves, and then the derivatives and integrals of vector function. Uh, and then for the next videos, I will discuss also the arc-length curvature and velocity and acceleration as applications of derivatives and integrals. Okay, so what are the intended learning outcomes for this specific topic? We have a lot of things to understand here. So we want to be at the end of this lecture, you should be able to analyze and sketch a space curve given by a vector valued function, and then analyze the domain range of a given vector valued function, evaluate the limit of a vector valued function, solve the the derivative and the integral of a vector valued function, and then apply the principles for solving the velocity and acceleration of a vector valued function. And then we want to solve the unit tangent vector, principal unit normal vector, the arc length, and the curvature. Okay, sige. Let's begin with vector functions. No? So, vector valued function is simply a function whose domain is a set of real numbers and its range is a set of vectors. So basically, you have an input, no? So the input are real numbers. Actually, you have t, no? T is the parameter, and then the output will be a vector in a space. So for three-dimensional vectors, so the definition of our vector valued function r of t, where r is a vector, no? Is just this. No? So for the x or the terminal points, we have the function of t or f of t, and then the g of t, and then the h of t. So as we recall last time, no, in our previous lessons, the t is just a parametric variable representing a domain, no, that could help us represent any line or plane, or to be more general, a function. Okay. So, for example, we have this vector valued function, r of t. Okay, so we want to find the component form of this function and its domain. So, how do we find the component form? So, basically, the component form is just a way to write the vector. So, instead of r of t is equal to this, no? So, we can also write this in its component form, wherein we have the I, J, and K unit vectors. No? So we have t cube, and then ln 3 minus t, and then j hat, and then plus we have square root of t k hat. Yeah. So that's it. That is the component form of the function. Now, how do we figure out the domain of this function? So for the domain of this function, what is the possible values of the parametric variable t? So what are the values of t here, no, that is possible to have a real vector value function. So as we can see here, the t here, no, in the I or the x coordinate will be any real number, no, any real number you can put to this, it will have a corresponding range that is a real number as well. But for this second coordinate, no, the ln 3 minus 2 minus t, the input, the argument here, that is 3 minus t, cannot be 0, no? So remember that when you have a value here, let's say ln of t, we it should be noted that t should not be equal to 0 or even less, no? So it should not be less than or equal to 0. Therefore, the t should be greater than 0 for this to have a corresponding value that is a real number, no? So you can try inputting in your calculator t is equal to 0, ln 0, or ln of a negative number. It will be an error, no? So meaning it doesn't have a real number as its range. And then for this one, what's this? Yeah. Okay, so for this one, we know that this one cannot be negative naman, no? So there's something wrong with my what's happening. What is So I cannot change. Yeah. So this should not be a negative number. No, it cannot be a negative number. So or let's say if you have a square root of t, the t here should not be less than 0. So this should be greater than or equal to 0. So therefore, the domain here, now the domain here, the t should be what? No? So if you have 3 minus t, I'm having a problem with my graphing tablet. So if you have 3 minus t, this should be greater than 0. Therefore, t, if you transpose this to the other side, the t here, I think t should be less than 3. No? And then for the other here, the other one here, if this is the square root of t, then the t here should be greater than or equal to 0. No? So if you can imagine a number line of t, so if we have here, let's say this is 0, we have a number line here, this is the positive side, sorry, this is the negative side. I think I have a problem with my tablet, no? And so this is the positive. Then therefore, if t is less than, no, t should be, you can write this as t is less than 3, no? This is the same thing. So the domain of this second coordinate, no, xy, is that t should be less than 3 only, no? So if this is 3, then it should be less than 3. And then for this one, t should be greater than or equal to 0, then therefore we have this portion as the domain of our z variable. And as you can see, no, it overlaps at this portion. Therefore, our actual domain should be this intersection, no, in between. So our t should be in between, no, in between 0, no, so 0 greater than or greater than, t should be greater than or equal to 0, but less than 3, no? Or we can write this as we have here 0 and 3. Okay, so this should be your domain. Okay, so take note of this, no? We have this and another one. If we have a rational function, let's say we have let's say 1 over t, then t should not be equal to 0. So remember the following principles in finding a domain. So the limits of a vector valued function. So let's say we have a given vector valued function. Then if we want to find the limit of this function, then we can find the limits of their coordinates, no, or elements independently. So if you want to find the limit as t approaches a, then you want to find the limit as t approaches a of the first function, and then the second function, and then the third function, and so on. All right. So a vector function R is continuous at a if we know or if the limit exists at this limit. Ano? So it is continuous at a if it has a limit or the limit exists at that limit. Yeah. Okay, so find the limit as t approaches 0 of R of t, where R of t is equal to this. Yeah. So to find the limit of this, then we can write this formally as this. So we have the limit, okay, the limit as t approaches 0 of the first function, we have 1 plus t cubed, ano? And then for the second function, we have the limit as t approaches 0 of t e raised to negative t. And then for the last function, we have the limit as t approaches 0 of sine t over t, and then that's that. So how do we solve a limit now? So basically we just substitute, no? So substitute 0 here. So we have here 1. Okay, so the limit is 1 for the first function, and then for this for second function, if we substitute here 0, this will be just 0, no? So we have here basically a 0 times e raised to negative 0. So this will be just 1. So 1 times 0 will be 0, no? So I can just write here 0. And then the last one, there are different ways to solve this. You can use the L'Hopital's rule, no? L'Hopital's rule, Or in general, this is actually a theorem in limits, no? So the value of this is equal to 1. But finding this using the L'Hopital's rule, finding the derivative of sine t, so we have here cosine t, the derivative of t is 1, and then evaluating this limit, no, as t approaches 0, so cosine 0 is 1, so therefore we have 1, 0, and 1 as our answer. Or in component form, we can also write this as I hat plus j hat. No? So our limit is also equal to I hat. Sorry, not j hat, but k hat. This is the z variable nga pala. No? Okay, next one, we have the space curve. So what we discussed last time is, we're only talking about the vectors or the vector r of t. Ano? But if we think about this, no, if this r of t, this is just the vector pointing to that terminal point. No? If we have a space curve, we can represent the space curve using this vector valued function. But to be specific, the coordinates of the terminal point of the vector valued function. So instead of a vector, we can write this as points. So depending on your value of t or your parametric variable, you can find or you can plot the space curve. So this is the same thing, no? This is the parametric equation. You can recall in your lines, this is the same thing. But in general, your functions here is not just linear. It could be any elementary function. So we have the algebraic, we have basically the polynomial functions, trigonometric, and so on. Okay, so describe the curve defined by the vector function around t. So we have 1 plus t, 2 plus 5t, negative 1 plus 6t. So we already discussed the lines, no? So the parametric equations of lines. So this is easy for us to understand. We know that this is already a line. We don't need to solve this already, no? But this is also a line. So now, what can we do, no? So we can visualize, no, to describe this curve. We can describe this by the definition of a line that is r vector of t, which is equal to r sub o plus we have t times the v. Okay, so here, as we can see, what is the value of this? Or what are the values of this? So this is your r sub 0. No? So r sub 0 is, the vectors here. The r sub 0 vector is 1. We have 2 and then negative 1. And then the v vector is, we have here, we have the 1, so the coefficient of t, the coefficient of 5t, and the coefficient of 6t. So we have here 1, 5, and 6. So basically, if you will draw this through a three-dimensional coordinate system, would be the coordinate system. Okay, yeah, sorry. Yeah. So if we have this initial point, r sub 0, or this initial vector, so this is x, y, and z. So positive x, positive y, and then z is negative. So we have here the p sub 0, and the vector pointing to that is our r sub 0 vector. And then the vector v, we can visualize that as let's say a vector similar to that will be something like this, no? So we have here this line, no? Yeah, so this will be your direction of this line. Yeah. Okay, it's somewhat hard to recognize, no? But this will be your linear function, no? So that is how we describe a linear vector valued function. Okay, so sketch the curve whose vector equation is, we have cosine ti plus sine t j, and then tk. Okay, now how do we do this? So in parametric equation form, we have x is equal to cosine t, okay, y is equal to sine t. So basically the coefficients of your unit vectors, ano? So z is equal to t. So basically this is your f of t, this is your g of t, and this is your h of t. Yeah. Okay. So what should we do here? Paano ba to i-visualize? So it is hard to visualize if it is in terms of the trigonometric function. It will be much better if we can convert this, no, this trigonometric function into something we are familiar with. So actually, there is a general form that is we have x minus h squared plus we have y minus k squared is equal to r squared. So this is the standard equation of a circle. And we can actually write this, no, into its parametric equation no? Parametric equation form. That is, we have x is equal to, sorry, not x equal to, but x minus h is equal to r cosine t, and then we have y minus h is equal to r sine t. So remember this, guys, no? So if you have a given equation that looks like this, you can write this in its parametric equation form that looks like this. And it is also applicable the other way around. So if you have this given function, so it should be cosine and sine together, no, to draw this circle. So therefore, we can rewrite this vector valued function or this parametric equation, or actually the space measure, into we have x squared, no, x squared plus y squared is equal to 1. So why is that? So because this is 0, so we have here x plus 0, comparing this to this, right? So h is 0, and then we have here a coefficient of 1, therefore the radius is 1. Yeah. So we can write this in this form. Therefore, what is this curve? So this curve is a circle, no? So we have the x, y, and z axis. Therefore, we have a circle here that has a radius of 1. Yeah. What about the t? So the t here is also a parametric variable. So if this is just these two equations, this will be just a cylinder. But since it has this z is equal to t, therefore the coordinate of z varies as t varies. So therefore, we can start with, let's say, x is equal to 0. Let's say t is equal to 0. So if t is equal to 0, then we have cosine 0 for x, no? We have y is equal to sine 0, and then z is equal to 0. So therefore, cosine 0, as 1, sine 0 is equal to 0. So therefore, the first point here is that we have, let's say, this is 1, 0, and 0. And then after that, we can form here a circle, but since the z is also varying, ibig sabihin the z is increasing, then it will form here a helical curve, so something like a spring. Okay, so this is the drawing of your vector valued function. So a better drawing is this. We have the first point when t is equal to 0, and then let's say up to t is equal to pi over 2. So if this is pi over 2, so we have here t is equal to pi over 2, which is also equal to c. And then this one is equal to when y is equal to sine pi over 2, we know that is 1. And then when x is equal to cosine pi over 2, which we know is 0. Yeah. Okay, so that is how you graph a space curve using the vector valued function. Okay, so we have another example here. So find the vector equation and the parametric equations for the line segment that joins the point P and Q. Okay, so how do we do this? So a vector equation that is a line segment. So how do we find the line segment? What is the formula for a line segment? So we did not discuss this in a deeper manner, but if you can recall, the line segment's definition is we have r of t, that is a vector in r. We have 1 minus r, 1 minus t, and then r sub 0 of, okay, vector lang pala to, and then plus t, and then we have r1 vector. And then this is, the domain of t here is only from 0, no? And then to 1. Okay, so what is this? So we can designate this as, let's say this is our r sub 0, and then this is your r sub 1. So therefore, to find this, we have 1 minus t, and then we can directly substitute now. So this is transformed only as a vector. Then we have r sub 0 is just 1, 3, and negative 2. And then plus, we have t times the vector r1, we have 2, negative 1, and 3. So distribute now, you can distribute this. We have 1 times this. So we have here 1 minus t. Distribute this to this. We have 3 minus 3t. And then distribute as well the last element of the vector. Then we have negative 2 plus 2t. And then plus, we have here 2t minus t. And then 3t. So adding this 2, so we have 2t plus 1 minus t, 2t plus 1 minus t, then this will be equal to, we have 1 plus t, right? And then we have here, so 3 minus 3t minus t, this will be 3 minus 4t, and then we have negative 2t, sorry, 2t, but negative 2 plus 2t, plus 3t, so this will be negative 2 plus 5t. Yeah. So this is actually your vector equation, no? This is not an equation, but no. This is your vector r, no? At the domain 0 to 1. But to have the vector equation, the vector equation here will be 1 plus t, and then I hat, plus we have 3 minus 4t, we have j hat, and then plus negative 2 plus 5t, and then k hat. Okay, so this is your vector equation. How about the parametric equation? The parametric equation is just the coefficients here now. So we have x is equal to 1 plus t, y is equal to 3 minus 4t, z is equal to negative 2 plus 5t, and so on. So this will be your parametric equation. So don't forget pala the domain, no? So the domain of your t should be only within 0 and 1. Okay, so include this as well. Okay, so we have another example. So find the vector function that represents the curve of the intersection of the cylinder x squared plus y squared is equal to 1 and y plus z is equal to 2. So what are these two things? So we have a given cylinder. Okay, so this is a cylinder. And then what is this? Okay, so this is actually a plane, no? So an equation of a plane. So we have an intersection of a cylinder and a plane. So how do we do this? So how do we draw this? So we already know how to draw this. So we have here a 3D 3D space. Then the cylinder here will be just this, no? This cylinder here with this cross section, a circle, no? So what we're trying to find is its intersection with the plane. So the plane could be tilted, no? In some way we do not know, no? I don't want to waste the time finding this or drawing this plane, but we can imagine, let's say we have an arbitrary plane intersecting this cylinder, so we can recognize that, let's say this is your intersection, no? You can imagine something like this. So the intersection of this cylinder and this plane will be some form of a circle, no? In its projection. So how do we do this now? So we know that if it is an intersection, for intersections, you have to recognize that we're just equating the x variable, the y variable, and the z variables, no? That is basically what we do in the geometry class, the analytic geometry class. So if we have this function, then we can also relate this to this other function. Now the problem with this is that it is an implicit function. We have to first convert this into its parametric form. So the parametric form of this equation, no? So in parametric form, okay, we have x is equal to cosine t. No? We recognize that this is the form, and then y is equal to sine t. So where did this came from? From the last slides, no? So if we have x squared plus y squared is equal to 1, then we know that we have x plus 0 is equal to r cos t. So r is equal to 1, therefore we have just cosine t. Okay, now we already have a coordinate for x and y, but for z, we can use this last equation, which is the equation of the plane. So we have z is equal to, so transposing this y to the other side, we have 2 minus y. Now, again, for intersection, we are just equating this 2. So therefore, we can equate this y is equal to y. We recognize that this y can be substituted here. So we have here z is equal to, no? So this can be simplified into z is equal to 2 minus sine t. So therefore, this is your space curve, no? So the space curve is, therefore, or roughly this is your parametric equations that represents this space curve. You can represent this also as a vector function. So the vector function here is, we have r vector is equal to, or r of t na lang, no? Is equal to, we have cosine t, sine t, and we have 2 minus sine. Okay? Right. Okay, it could be in component form as well, but I won't write that anymore, ano? So the domain of t, now you can think of the domain of t. You can think of the principal domain of t. So the principal domain of t can be different, no? But I can just say here that since a circle repeats, no? So if you have a circle, you can start with 0, no? So 0, and then 1 revolution is 2 pi. Sorry, so therefore we have a domain of from 0 to 2 pi, no? Or we can recognize as a closed bracket. So this should be the closed bracket. Anyways, okay, so t should be in between 0 and 2 pi. Okay. Next one, so find the parametric equations for the curve of the intersection of a paraboloid 4y is equal to x squared plus y squared plus z squared of plane y is equal to x. Okay, so we want to find the parametric equations of this intersection. So we have a paraboloid. Now, how do we draw this? So we want to visualize first the problem before we solve this, no? So a three-dimensional space. Ayan. And then this one. So we have a paraboloid. So how do we draw this paraboloid? So how do we do this? So we can assume a value of 0. Oh, what is the behavior? So if z is equal to 0, if this is 0, then we have a parabola. So if we look at this, no, if we have here top view, sorry, we just draw the axis, no. So if this will be x and y, so x and y, then this will be something like this, no. So a parabola that looks like this. So therefore, we can write this, no, this intersection here at this form, no, or a projection of this surface in this form, and then we can vary the value of z. So the z can be varied, positive values of z and negative values of z, and we can recognize that if we have a higher value of z, no, then it adjusts, no, it will adjust. So we have here 4y minus z squared is equal to x squared. Okay, and then simplifying this, we have y minus z squared over 4 is equal to 1/4 x squared. So what we can recognize here is that the higher the z, the closer or the it will transcend to a different point here, no? So if z is positive, then it will be the point. If z is negative, it will also be the point, no? Positive or negative. So it will adjust accordingly, and it will transcend to or translate to the other side. So we have here a parabola that looks like this, and so on, no? It's really hard to visualize this, no? So actually, the drawing of this is a surface that looks like this. It is a paraboloid. You can imagine a cone, no? So a cone like this, and this will be your paraboloid. Now, we have a plane. So the plane here is what? So how do we draw this plane? So if x is equal to y, then this will be, actually it will be looking like this. It is not perfect, but I can draw a plane here that looks like this. It's similar to this. Yeah, so this is the plane, and the intersection of this paraboloid and this plane will be this circle, no? So how do we solve this now? Again, for intersections, we just equate the x, y, and z's, you know? But how do we do that now? No? So we can equate here this y, since y is equal to x. So now y is equal to x, we can change this as x, no? So we have 4x is equal to x squared plus z squared. Therefore, we can simplify this now to the other side. We have x squared, so translate this to the other side. We have minus 4x. And then we have this positive or negative? This should be positive pala, no? Plus z squared is equal to 0. So we can form here, no? As you can see, we can form here a circle. So we can do the completing the square. So we have plus z squared is equal to 0. So we can add something here, and we can add also something here to make this a complete square. So to make this a complete square, we can add 4 here and another 4 to the other side of the equation. So therefore, this will be x minus 2 squared plus z squared is equal to 4. Therefore, we can see here that we have a circle. So this will be your h, no? This will be your h, no? H is equal to 2, and then we have k is equal to 0, and then your radius will be 2, no? So therefore, we have here, what we have here, no? This is a cylinder that extends here, no? Infinitesimal the other side as its projection, no? But we are only interested in this portion, no? So how do we find this portion? We want to first convert this. Again, we can convert this into its parametric form. This equation can be converted into its parametric form. So we know that x minus 2 is equal to, kasi we have a formula, diba? So we have, I can simplify this first now. We know that x squared plus y squared is equal to 1. And the derivation of this can be coming from the Pythagorean identity. This should be cosine, no? Cosine squared t plus sine squared t is equal to 1, no? So therefore, if this is the form, then we can equate this into this form as well. So we can rewrite this as, when dividing this by 4, we have here x minus 2 squared over 4 plus z squared over 4 is equal to 1. So we can rewrite this as well as, so we can combine this 2, we have here a greater parentheses. So we have 2 squared at the bottom, and also for this one, we have c over 2 at the bottom. So this one can be equated as cosine, no? And this will be equated as sine. So if we have this, then we have x minus 2 is over 2 is equal to cosine t, diba? Therefore, we have x minus 2 is equal to 2 cos t, diba? So x is equal to 2 plus cos t. So this is the first coordinate of the space curve. And then for the z variable, so we have z, no? So we have z over 2 is equal to sine t. So therefore, we have z is equal to 2 sine t. So therefore, this is your other parametric equation for describing this curve. Now, again, we know that x is equal to y for this to work. So therefore, your x is also, your y is also 2 plus, it should be 2, ano? I got to write it, 2 cos t. Ayan. Okay, so your parametric equation will be x is equal to 2 plus 2 cos t, y is equal to 2 sin t, and we have z is equal to 2 plus 2 cos t. Yeah. Okay. So what is the domain of the t here? The t here will be, so the principal domain, it could be any real number, no, but the principal domain will be You can classify this as from 0 to 2 pi, no? Yung t natin. Okay, so the visualization of a better graphical representation should look like this. So this circle right here, okay, the circle right here will be, we'll have a parametric equation of this point. Okay, so that's it for this video. Thank you guys, and see you for the next video.